Okay, hello. This is my work for our assignment for chapter number 16, where we're looking at the kinetics for a rigid body. We're looking at the forces and accelerations. So this is the first problem. And in this problem here, we have this piece of rod here that's a quarter of a circle, and it has a wheel on each end, and it's rolling in this track here. And the first thing it wants us to determine is the acceleration of this rod due to this force P pulling it to the right. And so we know that there's going to be no rotation because of these tracks here. And so in order to solve this, the first thing that I did was just draw a free body diagram here in my kinetic diagram with positive going to the right and up. And looking at this, we can use our equation. So I started with using the sum of the forces in the x and y direction has to equal ma at the center G. And so if we do that in the y direction here, we have the two reactions at A and B pointing upward, and that has to equal the weight going down. And so we still have two unknowns there that we're going to need to solve for. And then if we do this in the x direction, we know that the force P is the only force to the right in the free body diagram, and that has to equal our mass times acceleration. And we know the acceleration will be only in the x direction because of the tracks. And so for this, we know all of these except for A, which we can solve for, and so we can find the answer for part A. The acceleration of the rod is just our force P divided by the mass m, which gives us an acceleration of 3.2 meters per second squared. For part B, to find these two reactions, since we have extra unknowns here, I went to our moment equation. And I decided to take a moment at B here because that would eliminate the most of forces here. It would eliminate P and By. And so looking at the moment equation here, we know that this is not rotating, so this term would be 0. And so looking at the moments, we need to have a moment for W and Ay. And W occurs at the center of gravity G. And so we have to know that for a part of a circle like this, G lies at 2r over pi from the radius here over this direction. And so using that information, we can take r away from that to get the distance from B over. So we subtract r from 2r over pi multiplied by the force. So this is the perpendicular distance times the force. And then the same for A. It would just be the radius times the force. And then that has to equal our term here, which is r from B to G crossed into MA. And so looking at this term here is once again using this point here for the center of gravity, which we know is 2r over pi. And then we know A from here, and the mass was given to us. And so at this point, all we have to do is plug in everything we were given, leaving us with the unknown of Ay. And so just plugging this into our calculator and solving for A, we know that the reaction at A is 3.819 newtons upward. And then taking that number back up into our force equals mass times acceleration equation here, we can plug that in our weight and solve to get that By equals 20.706 newtons, also upward. And so that is the answer for problem number 1. On problem number 2 here, we have this triangular shape here, and it has two pins on it that slide in this circular track here. And the first thing the problem wants us to find is the acceleration of this triangle as it falls down. We're told the velocity of both of these pins, we're told the weight at the center point G here, and we're told the radius of these slots. And so first thing I did was draw a kinetic diagram here and set that equal to a Alright, I drew a free body diagram and set that equal to my kinetic diagram. And then, since we were given velocity here and we were asked to find acceleration, the first thing that popped into my head was using the equation here, the normal acceleration equals v squared over r. And so, plugging in our given velocity and radius, we can find the normal acceleration there and then convert that into feet per second squared. But then we also need the other portion of the acceleration, which is the tangential acceleration. And so in order to find the tangential acceleration, what we can do is look back at our diagrams here and recognize that on this side here, if we take the component of this that is in the cosine of 30 direction and set that equal to our mass times our tangential acceleration, because this would match the direction of our tangential acceleration. Then we can plug in what we have, the masses cancel, and we can find our tangential acceleration here. And then in order to find the total acceleration, we just use the Pythagorean theorem here. We square both of those and then take the square root, which gives us our acceleration of 30.56 feet per second. And then we also need the angle of that. And so by using the inverse tangent function and our normal and tangential acceleration, we're able to calculate that that is 84.1 degrees, and that will be down and to the right. And then, so that's the answer for part A. And then part B wants us to find the reactions here and here. And so looking at this, we know that the reactions will be normal to this slot. And so what I decided to do first was try using a moment. Because there's two unknowns here, we have the unknowns at A and B. And so by using a moment here at A, we're able to eliminate that unknown and try and find B. And so in order to do that, we know that the moments about point A, we have the force of B, which we're trying to find, as well as the component of G. And so that's what this is here. We have the force times the perpendicular distance, and then this one here is for point G here. So we have the 6 inches times the weight at G. And then we set that equal to the moment in our kinetic diagram here, which is our acceleration. And so I drew another diagram here to just kind of help me visualize that. We have our acceleration that we calculated up above right here, pointing in this direction, with our angle of 84.1 degrees. And so we need to find the moments for that about point A. And so we take the distance, which is 6 for the first one right here, and then multiply that by that component. So that would be sine of this angle, and then the other direction would be cosine of that angle. And then those are both multiplied by the mass, but we're given the weight, and so we have to divide that by 32.2, which is the acceleration of gravity. And then the vertical distance here is 3, so that's different as well. And then it's just a matter of plugging this into our calculator and rearranging it to solve for our reaction at B, which gives us a reaction at B of 1.285 pounds. And looking at the diagram here, we know that this angle is 60 degrees, and so that reaction force will have to be the 30 degrees. And then for A, we could either take another moment at B and repeat this process, or I decided to use the sum of the forces in the x direction. And so, similar process here, we have the sum of the forces in the x, which are reaction at A times cosine of 30 plus reaction of B times cosine of 30, and that gives us the forces that are in the x direction for both of those. And then we set that to equal to our acceleration component in the x direction, which is this times cosine of 84.1, and that's multiplied by the mass, which again is our weight divided by gravity. And since we have B right here, we can plug that in and then solve this equation for A, which gives us 0.505 pounds, and that's again in the 30-degree angle, just like B. And so that's it for problem number 2. Okay, this is problem number 3. On this problem, we have these two disks here, and we're told that there's a force that pushes disk A into disk B until they contact each other here in the middle. And initially, disk B here is at rest, and disk A has an initial angular velocity of 360 RPM. And the first thing this question wants us to find is the angular acceleration of disk A and disk B. And so the first thing I noticed looking at this problem is that this angular velocity was given to us in RPM. And so I took that and converted it into radians per second by multiplying by 2 pi and dividing by 60. And then I just drew a free body diagram and a kinetic diagram to help me think through the problem. We know that for a disk, that this is the value for I for a disk or cylinder. And so I wrote that down so we would have that. And then I labeled all of these forces. Looking at this, we know that there's going to be a normal force pushing back from this force that was 20 newtons that was given in the problem. And then there will also be a force of friction that causes these two to start to turn when they come in contact. And we're told that the coefficient of friction mu k equals 0.15. And so I started by creating a moment about point A here, the center of disk A, and filling in the values that we knew there. So we needed to know at A here, the only force that would create a moment is this friction force here. And so I realized that we didn't know that yet and we needed to figure that out. And so what I did was I used the sum of the forces in the x direction here on disk A. And there's only two forces here, which tells us that this normal force here, N, has to be equal to this force here, which is 20 newtons. And then if we do the sum of the forces in the y direction, we can find out what F is. And so we know that the force of friction is always mu times N. And since we just found N to be the same as this force here, and mu was given to us in the problem, we can find out that the force of friction going upward is 3 newtons. And so now that we have that, we can go back to our sum of the moments here that we were looking at and plug in the 3 newtons that we found for the force. And then the distance here to the center is 0.08 meters, converting that from the millimeters given in the problem. And that has to equal IA alpha A. And IA for our disk is right here, and so we plug in our known values for that. And then we can solve for our first alpha value, which comes out to 12.5 radians per second squared. And we know that that's going to be in that direction. And then repeating this for disk B here, it's very similar. We use the same friction force because it's in common with both disks. IB is the same formula, we just have a different radius because B is a smaller disk. And then we can solve that to find that alpha B equals 33.3 radians per second squared. And then that is the answer for part A. Part B wants us to find the final velocity of each disk, the final angular velocity of each disk, and we're given the initial angular velocity of disk A. And so looking at that, we know that we'll have this initial velocity here, and we need to find out what the velocity is at a certain time. And we know that sliding stops when this holds true. This is when there'll be no friction. And so that's the point we're looking for. And so to find out what time this occurs, we use this equation here that uses the alpha values that we calculated. And then plugging in all of our knowns, we know everything in this except for alpha. And so it just comes a matter of plugging everything in and finding out what time our angular velocity relationship here will hold true, which turns out to be 1.00531 seconds. And so using that, we can find out what omega is at any time. And so this equation here will allow us to find out what the angular velocity is of disk A at any time, and we want to know what it is at this time here when they stop sliding, when there's no slip or friction. Okay, so for problem number 4 here, we're asked to determine the radius of gyration for this drum and this disc that are attached together. We're given the tension in both of these ropes, we're given both radiuses of the disc and the drum, and we're given the mass for this entire system here. And so the first thing I did to solve this was just list out some of the knowns that we have that were given to us and draw my free body diagram and set it equal to the kinetic diagram. And so in order to find the radius of gyration, we know that I has to equal mr squared, and r would be our radius of gyration, which I called k in this problem. And so in order to solve this problem, the first thing that I decided to do was sum the forces in the y direction. And so we know that the sum of the forces in the y direction have to equal mass, which was 5 times the acceleration. And in the y direction we have these two forces, which add up to 60, and our weight pulling down, which is the 5 times 9.81, which is right here. And so plugging all of that in, we can solve for our acceleration. And then using this relationship here with alpha, we can solve for what A is. And so now that we have those two relationships there, and then the next step to this problem was to take a moment at G, our center, and that means we don't have to worry about the weight here, but we need to do the force times the perpendicular distance for these two tensions here, which is what this is here. We have our radius times our force, and we know that that has to equal this term right here. And since I've already calculated alpha, we can plug that in, and then we can solve this for our radius of gyration k. And so just solving that equation gives us our value for k of 170.9 millimeters. And so now that we have that value for the radius of gyration, it would be a lot easier for us to calculate further things using this for the value of I. On problem number 5 here, we're given this what they call a uniform slender rod. We're given the length of this rod, and it pivots at this point C here. And then we're given the distance r bar from this pivot point to the center of gravity, center of mass G. And so the first thing that the problem wanted us to find is the angular acceleration of the rod, which would be alpha. And then it also wants us to find the components of the reactions at C. And so the first thing I did was just draw the free body diagram and set it equal to the kinetic diagram, like we do in every problem. And I labeled all of my forces here. We've got our reaction forces at C, we've got our weight pulling it down, and then the force P, which is given to us of a force of 75 newtons. And so I started by using the equation sum of the forces equals mass times acceleration, and I did that in the x and y direction. So when I did that in the x direction right here, I realized that I didn't know this term here yet, and so I couldn't solve for this reaction Cx yet. So I just stopped there and knew that I had to look for another equation to help me solve that. But in the y direction here, we know that this is in line here with our pivot point, and so that would be 0. And so solving this, we know that the reaction at y has to equal our weight, which is 5 times, or it's gravity times our weight here of 4 kilograms, which comes to 39.24 newtons. And that is in the opposite direction of our weight, or upward to balance that. And then to find the angular acceleration of the rod, I decided to use a moment, and I chose point C here, so it would eliminate both of these reaction forces and our weight, so we would only have to take a moment about P. And so to take the moment there, we need to know the distance from this pivot point here to this force P. And so if we look at our diagram here, we know that that has to be r bar plus L over 2. And so that's what I have here is L over 2 plus r bar, and then multiplying that by our force P of 75. And then that has to equal I alpha. But since we're taking the moment about somewhere other than the center here, we have to add in this term, r times r cross ma, or just r times ma. And so plugging in what we know here, we know everything on this left-hand side of the equation. We can plug it in and get 50.625. On the right-hand side of the equation here, we know I alpha for a rod has to equal 1/2 m, or 1/12 mr squared. And then we don't know this term here, but we do know that our acceleration has to equal r alpha because it is in the tangential direction. And so we can replace that with r bar times alpha. And so that means we have no unknowns in this equation except for alpha. And so just simplifying this other side of the equation, we can get this equation and then solve for alpha. So alpha turns out to be 107.1 radians per second squared. And then from there, going back up to this equation where we didn't have enough information, we can plug in that r alpha right here and move P to the other side. And so we have this term plus P has to equal Cx. And so plugging that into our calculator, we know that the reaction force Cx has to equal 21.39 newtons. And so that's the answer for this problem. We have alpha for the rod as well as the two reaction forces at C. For problem number 6 here, we have this tire, and we're not actually given numbers in this problem. It just wants us to derive an expression for the acceleration of this wheel in terms of r, k bar, beta, and g. And so this is the free body diagram and the kinetic diagram I have here. So we have this point of contact here. It's going to have a friction force and a normal force, and I labeled that point A. And then we have our weight pulling us down at the center of mass G, and that has to equal our kinetic diagram. And then I also wrote these equations up here, so we know that I, for our instance here where we want to find k bar, we can say that I alpha equals m k bar squared alpha to get this in terms of what we're looking for. And then for the second part of this, we have mass times acceleration, and we can replace acceleration with r alpha because it's tangential. And so to solve this problem, I decided to take a moment about this point A right here. And so if we take a moment about A, we have our weight times sine of this angle beta that's unknown, but we know that it has to be sine of that angle, times our radius r is the distance from A to G, and that has to equal I alpha plus this term here, MA cross R. And then what we can do from that point is just plug in these relationships that we know here, which gives us this equation. And then we know that weight is m over g, and so that gives us this term for g. And then all we have to do at this point is just simplify this and solve for alpha. And so rearranging this equation for alpha gives us this, and then we can simplify this to get that we know our acceleration, which we're looking for, is r alpha. And so we'd take an alpha term over, and that gives us this for our final answer for this problem. Okay, so this is problem number 7 here. In this problem, we have another drum here that's attached to a disc, like a previous problem. And the first thing the problem wants us to find is if this disc slides or not. And in order to know if the disc slides, we need to know if this friction force between these 2 points is greater or less than the force from the disc or the drum. And so the first thing I did here was just draw my free body diagram and set it equal to the kinetic diagram. And then from there I just pulled out some of the information from the problem. We know that the radius has to be converted to feet. And we know that this term AX is tangential, and so it will equal R alpha. And then for our I term, we can use the equation m k bar squared to equal I, and that will help us in our calculations here. And so we can actually just calculate I up at the beginning here, so we have that for when we need it later on when we're taking moments. And so dividing by gravity gives us our mass, and then multiplying by our radius of gyration, which was given to us, gives us our term for I. And we know we can use this I because we were given the radius of gyration that allows us to use this equation. And so from there, what I decided to do was take a moment where the ground meets this disc here and see if we could determine some of the forces at play in that area there. And so to take that moment, we know we have this term here, which is our distance times our force, and that has to equal I alpha plus MA cross R, or R cross MA. And then we can use these equations, or these relationships that we put up here, in order to simplify this. So we know I, which we calculated here using the radius of gyration. And so we can plug that value in for I. And then we also know both of these terms. And so plugging those in, we can solve for alpha. And alpha turns out to be 7.73 radians per second squared. And then we can take that term and plug it back in here into this relationship to find out what this value is, our acceleration in the x from the center of gravity. And then once we've taken a moment, we can also take our equations for force in the x and y direction. And so if we apply some of the forces in the x direction, we have just this force F here is our only unknown, and that has to equal mass times acceleration. And so using the acceleration that we calculated here, that we got from plugging alpha in, we can find our mass by dividing by 32.2 again by gravity, multiply by our acceleration, and find out that force is 1.6 pounds. And then doing this in the y direction, we can try and find this normal force here, which will help us find the force of friction. And so calculating the normal force here, we have weight pulling down, this P going up, and then our normal force would point up as well. And so putting those three values in here, we can find that N equals 5. And then we know that our force of friction is mu N. We start by using our static friction of 0.25, which gives us a force of friction of 1.25. But since that is less than this force that we calculated here, we can tell that this force will overcome that force of friction, and the disc will be sliding as it moves. And so that is the answer to part A. And then since it does move, we need to recalculate this force of friction using mu of k, because we know it's not static friction anymore, which gives us a force of friction of 1 pound. And then for the next parts of the question, we need to find the angular acceleration of the disc, or alpha. And so taking a moment at G will allow us to do that. And so there's two forces we need to account for there. So we have our force P times this distance, plus our force F times this distance. And our force F is what we calculated up here. And then we set that equal to I alpha, but we know I, we calculated that up above. And we know F from right there, and so we can calculate alpha by just plugging this into our calculator. So we get a value of alpha of 12.88 radians per second squared, and it's in that direction. And then once we have alpha here, it's a pretty simple matter of calculating the next thing, which is the acceleration of G right here. And so all we have to do is sum the forces in the x direction, and we have our force, which is the same here that we calculated, and that has to equal mass times acceleration at g. So our acceleration at g, when we plug that into our calculator, comes to 3.22 feet per second squared. And so that is all for problem number 7. Okay, so this is problem number 8. It's the last homework problem for this assignment. And in this problem here, we have these two discs labeled A and B, and we know that they are the same diameter here. They're uniform discs. And we also know that they are connected by this rod at a pin at A, at C, and a pin at D. We're also told that there's a moment on disc A here, which is shown here. That is 2.25 Newton meters. And the first thing that this question wants us to find is the acceleration of the center of each disc. And then it wants us to find the force component at this pin D right there. And so in order to solve this problem, I decided to look at each of these three bodies here individually, and then we can create a system of equations that will allow us to find any of the questions that the problem wants us to find. And so to start off with here, I just listed some of the things that we know that will be useful to us as we continue through the problem. This is the weight that we were given, and we were also given the I for the disc, which is, since it's a disc, we know that the I value will be 1/2 mr squared. And so this is the total mass, because we know that there's 2 kilograms for each. And since these are uniform in every way, that really simplifies our problem a lot, because we can deduce that the angular acceleration of A will have to equal the angular acceleration of B, because they're connected and they're uniform. We also know that the center of mass here and here, the acceleration of those 2 points will also have to be equal, and that our acceleration has to equal r alpha for both of those instances. And so this is the free body diagram that I drew for disk A. So there's the moment that I labeled that was given to us. We also have the force at C due to this rod. We have our weight at the center of mass going down. And then I labeled a point J here, which is the contact point between the ground and this rod. And so first thing I did with disk A is take a moment about this point J. And doing that, we have our moment here, which is positive. And then we have the moment due to force C here, which would be the other direction, it would be negative. And then the distance between them is the 0.08, converting millimeters to meters. And that has to equal I alpha, so we can take the I value that we listed up above and plug that in. And then since we're not taking the moment about the center here, we have to add this cross product term in here, and then the acceleration can be replaced with the r alpha that we talked about above. So this term can simplify to m r squared alpha. And then it's just plugging in a lot of our given information into this equation here, and simplifying that, we can create this equation here. But there's 2 unknowns. We don't know C and we don't know alpha. And so we repeat this process with disk B in order to create another equation that will help us find those unknowns. And so for disk B here, we have a similar free body diagram and kinetic diagram, except the disk B does not have the additional moment, and the force D is pointing in the other direction. And so looking at that, we can create an equation from the moment at the ground here, which I called O. And so, like I said, there's no moment, so our moments are just D times 0.08. All of these others go through our moment center, so we ignore them. And then the right-hand side of the equation is identical to what we had up above. We have our I alpha term right here, and then MAR, which can, this acceleration can be replaced with R alpha to give us the R squared alpha term. And then we plug in our given information, and that creates this equation here. And then I like to keep track of our unknowns and equations as we work through these. And so looking at these 2 equations here, we can tell that we still have 3 unknowns and 2 equations. We have C, D, and alpha, and so we're going to need to create another equation using this rod here. And so creating a free body diagram of the rod looks like this. We have those 2 forces here, which are the reaction forces from D and C up above. And that has to equal mass times acceleration of the center of the rod. And so looking at this, we can use this kinematic relationship here in order to get this in terms of alpha here for the acceleration of the rod, which is AR, and relate that to these 2 accelerations. And so doing that, we can look at this diagram and recognize that all of these forces are acting in the x direction. And so using the sum of the forces in the x direction has to equal mass times acceleration, is what we have here, plugging in what we found from up above. And then we can simplify this to find this equation here, that C minus D equals 0.2 alpha. And so now this simple equation here that we were able to derive will help us to find what the question is asking us to find, because we now have 3 equations that I've starred here and 3 unknowns, C, D, and alpha. And so using these 3 equations, we can solve for any of those unknowns. And the one that the question is asking us for is D. And so solving these 3 equations, we can find that D has to equal 11.87 newtons to the left. And then from there, The acceleration of the center of each disk, like I stated up above, we know that those are the same. And so if we solve for the acceleration of disk B, that will be the same as A. And so plugging in everything we've been able to solve for up to this point to get the acceleration of B gives us 2.64 meters per second squared. And that has to be to the left. And so since those are the same, we now have answered both A and B for this question. So that's all for this homework assignment. Thanks for listening. Bye.